AQFT on subfactors and K-field.
Okay. First of all, I'd like to thank the organizers for inviting me to speak on this special occasion. Detlef asked me to talk about the impact of AQFT on operator algebras. I'd like to do that from two viewpoints. One is subfactors and twisted K-theory. So what's new in this talk is in these two preprints here. So I'll start with really neither of these topics, going back one step to statistical mechanics. So to be concrete, I'll work with the Ising model, two-dimensional, nearest neighbor. And if you write down the partition function, one way to compute that is through the transfer matrix method. So here I've written down that the transfer matrix T for the partition function on a column. So if I have boundary values on the left and the right, that'll give me a matrix. There's a plus minus option at each site, so that gives me something like 2 to the n matrix algebra. So it's an element in a Pauli algebra, and you can decompose that according to interactions along the rows and the columns. So that's a matrix product like this. If you take the logarithm, you have some quantum Hamiltonian. So you can be very explicit here and write it down in terms of these Pauli matrices. So the transfer matrix is made up of two parts, V and W, with these parameters K and L, which depend on the temperature. So at zero temperature, the transfer matrix is exactly V, this part here, which has a degenerate largest eigenspaces of, say, all pluses or all minuses. And at the other extreme, at infinite temperature, T reduces to W, and that has a non-degenerate largest eigenspace of an equal distribution of plus and minus. Right, so this allows you to go from a two-dimensional classical model to a one-dimensional quantum model based on this Pauli algebra with this one-parameter dynamics given by the logarithm of the transfer matrix. So, for example, if you have an equilibrium state on the classical model, it gives rise to a ground state for this one-parameter dynamics, and you have differing behavior at zero temperature or low temperature and high temperature, and something happens in between, which you can actually trace back to a K-theoretic object, which is what I did with Fujihiro and John Lewis. So as I said, for zero and infinite temperature, you can compute explicitly the transfer matrix. Hence, you can write down the corresponding ground states at zero temperature. There's two of them with plus or minus spins, and then there's this infinite temperature ground state of equal distributions. So as I said, K-theory already enters at this point through basically a mod 2 Fredholm index, which goes back to T.S. Singer. But the way I'll look at it here is through this endomorphism nu, which relates zero and infinite temperature, which basically relates these two components of the transfer matrix, the V's and the W. So it basically tries to interchange those as much as it can. All right, so the transfer matrix, in particular the V's and the W's, were made up of these two kinds of operators, the sigma z's and the products of sigma x's. So you can write down an endomorphism on the Pauli algebra which interchanges these things. Or at least, to do it carefully, when you you interchange sigma x with a sigma zj, but when you go back in the other direction, there's a shift by 1. Okay, that endomorphism is only defined on, say, the sigma z's on the product of the sigma x's. So if I have a grading where sigma z is odd, sigma z is even, and sigma x is odd, this is really only defined on the even part of the Pauli algebra. If I want to extend it to the whole Pauli algebra, I have to do something on the individual sigma x's, and you can do it like this by some kind of Jordan-Wigner transformation. That enables me to extend this endomorphism from the even Pauli algebra to the Pauli algebra. It's not quite a square root of the shift. It's only a square root of the shift on the even algebra. But because of this Jordan-Wigner mess here, when I square it on a sigma j, I pick up this initial contribution here. Okay, but that's all right. The best way to understand that is to lift it even further to an infinite algebra. So I go to a Kunst type algebra generated by two partial isometries, S plus and S minus. So the even Pauli algebra, the Pauli algebra is generated by products of S's and S star. We have the same number of S's and S stars. And then I can define this high temperature, low temperature duality not only on the Pauli algebra, but I can lift it all the way up to this infinite algebra by this combination here. That defines it for me on sums and differences of S plus and S minus, hence on everything. That's an extension of the square root of the shift on the even part of the Pauli algebra. And it's got some nice properties. So what this enables me to do is to find three endomorphisms of this infinite algebra, which I've labeled here as vertices of a Dynkin diagram A3. So that there's the identity. There's alpha, which is an automorphism, which just interchanges the plus and minus states. And then there's this high temperature, low temperature duality, nu, which I've introduced in this long-winded way. And when I take the square root of this, when I take the square of this up inside this infinite algebra, I get this decomposition in terms of S plus star and so on. S sigma is a generator, so this formula here has to extend to everything down here. I interpret this formula here as a copy of the identity and a copy of alpha. So that really means that in this block decomposition here, I've got nu squared as the identity plus alpha. So I forget about everything else, and then I focus on these relations here. It's a construction of sectors on this infinite algebra here, which reproduces the fusion rules described by this Dynkin diagram A3. So in other words, the vertices are labeled by these three endomorphisms, and the edges represent multiplication by this fundamental element nu. So nu times the identity is obviously nu, and so on. And nu times nu squared, is the sum of the nearest neighbors along the edges. All right, so in this way, I'm associating to this Dynkin diagram, which has something to do with the representation theory of SU2, endomorphisms of some infinite algebra. So originally, you could think of these as the states that I'm putting on the statistical mechanical model. But in this subfactor approach, they are thought of as endomorphisms of some type 3 factor. And in the K-theory side of it, these vertices will represent or be represented by twisted bundles. Okay, so I'm going to look at these partition functions in some kind of continuum limit. So I take the partition function of this square, decompose according to columns. So that's matrix multiplication by my fundamental column vector T. And if I've got periodic boundary conditions on this torus, that closes up to a trace. Then when we take some continuum limit, I get some field theory on a torus, and this trace of matrices is now going to a trace on an infinite dimensional space with some generators L0 and a commuting L0 bar. And if I decompose according to some basic symmetries of my Hilbert space, labeled by some irreducible objects, lambdas, this will decompose as a quadratic expression like this in the characters. And if this is supposed to represent a field theory on a torus, it should not depend on how I reparameterize the torus. In other words, if I take fractional linear transformations on the tau here, in this way, the partition function should remain invariant. So these labels that appear here, the lambdas and the mu's, they come from decomposing my infinite dimensional Hilbert space according to some underlying symmetries. So in practice, that could come from some positive energy representations of some loop group, as in something like here for SU3, or for Dynkin diagrams for SU2. And then this modular invariance translates to a question about matrices. I'm looking for matrices in the commutant of some SL2Z action because of this. There's an underlying SL2Z action on matrices. And then because these coefficients arise as multiplicities of Hilbert space decompositions, they should be positive integers, and usually with some normalization because of uniqueness of the vacuum. But in practice, it's often convenient to drop this assumption. Okay, so just to be more concrete about exactly what this is saying in the Ising model, I've got 3 vertices on my Dynkin diagram, and so there should be 3 positive energy representations, or 3 representations of these chi lambdas. So you can write them down concretely using the transfer matrix formalism I suggest, I sketched. And then you can write them from Pauli algebra, obviously in terms of fermions, and you can do it in terms of either half integers or integers. In this line here, this Hamiltonian will not give you an irreducible object. You still got to decompose according to a parity. So there'll be 2 irreducible representations, chi plus and chi minus, coming from this Hamiltonian, whereas this one corresponding to free boundary conditions is already irreducible. So those are my 3 chi lambdas. So because of these fermion descriptions, you can easily compute what the characters look like, and then you can even take fractional linear transformations on these taus and see that these 3 characters transform linearly under the 2 generators of SL2Z, which are over here, and you get these 2 matrices describing the transformations on the characters. So that's what we look at in practice, is a representation of SL2Z by finite matrices, which looks like something like this. T is diagonal, S is symmetric, and one column or one row always has strictly positive entries. So that then you try to find the commutant of this representation, and then amongst those look for the matrices with positive integer entries, and try to classify them. So in this particular example here, there's only one solution, the diagonal matrix. All right, so that's the framework. We try to classify or understand modular invariance in this definition here, and the lambdas and mu's, which represent the labels, which originally were something like positive energy representations, are now thought of as endomorphisms of a type 3-1 factor, satisfying some fusion rules. They're not commutative, but they are as sectors. In other words, there's a correcting unitary which can be chosen carefully, so that if you write it as a braiding like this, then you've got the Yang-Baxter equation, braiding fusion, and so on. And then once you have a meaning for this kind of crossing, you can write down a representation of S and T using a hop flink and a twist like this. And that should correspond to the S and T matrices which you had from the positive energy description. Okay, so that's the framework, and then you need examples, and that all comes from AQFT. Right, so here these lambdas, the pi sub lambda is a positive energy representation of some loop group. You restrict to some proper sub interval I of the circle. I primed is the complementary interval, and so we have an inclusion of factors like this. Now, this you can read off as follows. If you're in the vacuum, then this isn't a proper inclusion. It's actually an inequality, and it defines a single type 3-1 factor. And then I read off this inclusion as this is my n here, and this is the image of this algebra under some endomorphism L lambda. And this construction, or this analysis due to Anthony Wasserman, gives us examples of braided systems with endomorphisms labeled by positive energy representations. And the braiding, for example, is purely geometric. It uses locality to move things around, and there's two ways to do that, which allows you to keep track of what's over and what's under. Now, there's another family of examples which come from quantum doubles of systems which are not in themselves braided. So in the first set of examples here, the positive energy representations, or the labels, have something to do with dinking diagrams like this, which come from something like the representation theory of SU2, or at least with a cutoff. Whereas in the second set of examples, I've doubled everything up in order to get a braided system, and especially a non-degenerately braided system. So the labelings won't be a single parameter, but there's a doubling, and I'll come back to that over and over again. Okay, so that's the the framework, and then I'll quickly go through the subfactor description of modular invariance. So you can think of it entirely in terms of restriction. So I'm going to start with a system of endomorphisms on some algebra n, described by a set A, which could be the vertices of some Dynkin diagram. And then I want to understand modular invariance through some kind of inclusion like this. So I want to look at expressions like this, quadratic expressions. And I said that you've always got the trivial diagonal invariant. So that's always there. Sometimes that's the only one. But you can modify this slightly by throwing in a permutation of the fusion rules, this sigma. As long as it's consistent with the S and T matrices, then that should give you another modular invariant. So suppose you could extend your system. So my algebra n is now embedded in an algebra M, where I have another set of endomorphisms up here, where I can use this system to write down a diagonal or maybe a twisted diagonal invariant here. And then I restrict my system down here down to n. So in terms of characters, it would look like this. But I'm really going to interpret this in terms of endomorphisms. So that means, in particular, if I take the character of the vacuum up here, that should decompose into characters down here. So in terms of endomorphisms, the basic bimodule or the basic endomorphism upstairs has to decompose as a sum of lambdas. So that's the least you need in this situation. So if you've got that, then at least formally you can write down these expressions here. You can take a quadratic expression upstairs, use these branching coefficients, and get some modular invariant downstairs like this. And basically that's all that can happen. Now there are some issues to be addressed. For instance, you might start with, say, in the loop group setting, this is really not just a single subfactor, but a family of factors n labeled by some intervals I, and those are local. Now, so you might then have an extended net up here, but in general, this extension is not going to be local. It may be in some situations, say, a conformal embedding where I'm embedding my group into a bigger group, and so I'm doing this Wassermann construction twice. All right, so locality in the extended net is not guaranteed, and there are different ways of characterizing this. One is that the extended net is local exactly when the basic endomorphism or the basic bimodule upstairs is not just any sum of lambdas, but this combination here given by, say, one row of or one column of the modular invariant. So it's implicit in what I'm saying here that if your extension is local, then the modular invariant is symmetric. But there are certainly non-symmetric modular invariants. And to handle those, you've got to go outside this local extensions. And the proper way to do that is to not to just have one embedding, but you need two intermediate subfactors coming from this kind of local extension, where in one case I use the column, the other case I use the row. And in that way you can understand completely modular invariance. Okay, so I just want to emphasize that this concept of locality you can use even when you're not talking about nets. So I think I'll skip that. Right, so I've talked about it in terms of restriction. In practice, you don't have the extended system. So we have to use some kind of induction instead. And this is what John was talking about yesterday. This is alpha induction. So instead of restricting, you induce from a system on N to a system on M using the braiding. Since braidings come in pairs by reversing the crossing, I don't have one induction, I have two of them. And I have to use both to really understand these modular invariants. So if I use the plus induction, I have this kind of set of endomorphisms up here, and the red one, say, for the minus. And then I let the blue denote the intersection. And then it's only the blue, the intersection, that I need to compute the modular invariant. So there are two kinds of endomorphisms here on the bigger algebra. I decompose into irreducibles and I count the number of common multiplicities. That's a positive integer, and then the claim is that this is actually a modular invariant. Of course, this needs some assumptions, but it only needs, first of all, this notion of the braiding, and secondly, that basic assumption that the M restricts to N is a sum of lambdas. That's all I need. Okay, but then that's not the end of the story, because this doesn't tell you when you've exhausted all modular invariants in this way. That seems to be the case for SUN. And it's known for SU2 and SU3. And even then, it's not clear how you're going to find systematic ways to construct inclusions which are going to reproduce either a given modular invariant, one which you know about, or exhaust all modular invariants. So that's one of the motivations for taking this over to K-theory, where the lambdas and the mu's will be elements of some twisted K group. And then you've got all the machinery of KK theory, Kasparov theory, spectral triples to help you try and construct modular invariants. Okay, but there are two other kinds of objects associated with this kind of inclusion. One is this basic NM sectors obtained by decomposing the I lambdas into irreducibles. So that's some kind of invariant which you can associate to the inclusion. And in the case of SU2, this is going to give me the ADE classification of SU2. Now there's another thing I have to take into account, and that's I also generate MM sectors upstairs by the ones downstairs. I can do it in either by writing down these combinations here and decomposing into reducibles, or as suggested by this picture here, I can take my alpha plus and my alpha minus, take all sorts of products, and as long as your braiding is non-degenerate, you get the same answer. Now there's another way of looking at this. If I call this NM system a classifying graph for my modular invariant, I can take Z star. That's also a modular invariant. It commutes with the action or the representation of SL2Z. The only thing that may not happen is that this combination may not be normalized to be 1 at the vacuum. But apart from that, it's a perfectly valid modular invariance. So you can ask whether this modular invariant can be represented by an inclusion. As long as Z is, this is. And it's a kind of basic construction in the sense of subfactor theory for modular invariance. And then the classifying graph for that, this is CIZ for Capelli, Itzig, and Zubair, is identified with this picture here. And then this product may decompose into normalized modular invariance, and that's described by these sheets here. Okay, so that's the framework in subfactor theory, and there's going to be a parallel description using twisted K-theory. Okay, so I just want to be a bit more concrete with some examples. So the Valinde algebra, that's this representation of say endomorphisms by multiplicities like this. I can write that as a single matrix, and this gives me a family of commuting normal matrices. Any such family is always diagonalizable, so I can write it in some kind of expression like this with some eigenspaces and some eigenvectors. And the mystery or the deepness of the Valinde formula here is that the eigenvalues and the eigenvectors are completely described in terms of this modular matrix S. Right, so that's the Valinde algebra described by these eigenvalues. Now, a subfactor is going to give me a representation of this Valinde algebra because NN, this system here, acts naturally on the one-sided system. So that means I've got a representation of this commutative algebra with this spectrum. So any representation must look something like this, but the eigenvalues have changed, that's all. And some of them may not be there, or they may be with increased multiplicity. Okay, and then the subfactor theory tells us that this multiplicity is described exactly by the diagonal part of the modular invariant. So in small rank like SU2, that's all that you're ever going to need, because for small graphs, if you know the eigenvalues, you know the graph. But that's not the case in higher rank. But this is what I mean by an IMREP. It's a representation of the original Valinde algebra by non-negative integer matrices. And this gives exactly, in the case of SU2, the ADE classification. So I'll just remind you what the ADE classification is all about. Now, there are ADE classifications everywhere. One is for finite subgroups of SU2. So these are the affine diagrams of norm exactly equal to 2. Now, this isn't exactly what's used in the classification of SU2 modular invariance. You've got to remove one vertex that reduces the norm to be less than 2. And so you've got pictures like this, the non-affine ADE case. So this is a description of all the diagrams or the NIMREPs which appear in SU2 at level 10. Right, so I've drawn the 3 diagrams, and the numbers underneath each one of them, if you insert them in this formula up here, that'll tell you exactly what the eigenvalues of those 3 graphs are. Or you can turn this on its head. If you see the numbers 0, 3, 4, 6, 7, 10, then you should immediately think of the Dynkin diagram E6. Okay, and so that's what Capelli, Itzig, and Zubair did. They found these 3 modular invariants for SU2 level 10. And so, for example, down here, this is one modular invariant. And if you look at the diagonal part, you get exactly those numbers which I had on the previous transparency. So that led them to associate, for that reason alone, this Dynkin diagram, E6, with this modular invariant. But the subfactor theory gives you a conceptual explanation of why it's really there. It's the NIMREP for the action of the NN system on the NM system. Okay, so that's the subfactor approach. Now I'll switch to a K-theory picture. And I'll do it first for SU2, but even before that, let's just go back one step to the maximal torus T of SU2 and start computing fixed point algebras. Because when I replace this by SU2, my Boltzmann weights in my original model are lying in this kind of algebra. All right, so let's compute the K-theory of this fixed point algebra. Well, first of all, let's just compute the fixed point algebra. So I do it step by step. And I have to take the commutant of this matrix, and I get C plus C. Then I go to the next step. I take this tensor product, I decompose. And then the commutant of this is the sum of three matrix algebras like this. So if I carry on, I'll get Pascal's triangle. So what do I mean by K-theory? I mean the group generated by the dimensions. So back here, I have C plus C. Well, the only possible dimensions in C are, say, 0 and 1. And I think of that as generating a Z. So I associate a Z here and a Z there. And here, in 2 by 2 matrices, the possible dimensions are 0, 1, 2. That generates the group Z. So on this level, I'll have 3 copies of Z. Those are the possible dimensions. And so as I go down Pascal's triangle, I'm picking up more and more copies of Z. So I'll have an infinite number of integers to describe all my possible dimensions. Where you can keep track of that just by writing down polynomials in an indeterminate T. And in Pascal's triangle, I associate this polynomial here to the mnth place in Pascal's diagram. And these things generate my ZT. Now, similarly, you can do the same thing for SU2. As I go further and further in this diagram, I'm picking up more and more copies of Z. So it should be another infinite number of copies of Z. But it comes in a slightly different way because it comes from the representation of SU2. So the polynomials associated down here have things to do with these Chebyshev type polynomials, which reflect the fusion rules of SU2 rather than T. So as groups, the K groups are the same, but if you really want to keep track of why the K groups are different, you have to look at them as ordered groups. And that means that I need to know which elements apart from 0 are positive in here, and you can keep track of that. But that's not what I need here. All I need is that the representation, the dimensions of the fixed point algebra have something to do with the representation theory of SU2. Okay, so that's just the Valinde algebra at infinite level. So if I introduce a cutoff, as I have over here, then a long time ago I showed with Jeremy Gold that the K-theory of that fixed point algebra is really exactly the Valinde algebra at level K when you divide out by, or you make this cutoff over here. Okay, but more recently I realized that the way to understand this is as equivariant K-theory. So I think of this as the equivariant K-theory of the Pauli algebra under this action of this quantum group. So that's the first suggestion, that K-theory has something to do with this Wallinder algebra. Now, Fried, Hopkins, Tellerman understood this in a slightly different way. Instead of taking a non-commutative algebra here, they took just SU2 as a space, and instead of taking the adjoint action here, they took the conjugate action of SU2 on itself, and then took the K-theory of that. But up here, I took the twist on the quantum group. They took the twist in the sense of twisted K-theory, which means taking bundles of compact operators. Okay, so let's I think I'll skip this. Right. So I want to think of G acting on G, and I need to try and motivate why this has got anything to do with the Wallinder algebra. So in operator algebras, what we would do is to realize my group G as automorphisms of some infinite algebra N with some associativity, but not necessarily a homomorphism property. And this means that I've really got a 3-core cycle, and every 3-core cycle arises in this way for some action like this. This means that an intertwiner space between nu GH and nu G times nu H and nu GH is one-dimensional. It's a line bundle. So if I write down an intertwiner space between these two things here, it's just different ways of writing nu HA. So the intertwiners are going to be generated by products of U's like this. Okay, so that I can keep track of by writing down these tubes. I have an A here and an H, which takes me to its conjugate. That is really this action of G on H. So these, if I let T denote this product of these two U's, this fundamental intertwiner, then because I'm really working in one-dimensional space, the products of these two T's written in different ways have to match up to a scalar. So that means that this, this formula here is really giving me a projective representation of this kind of picture here where H acts on A. So in other words, I've got a 2-core cycle for the action of G on G by the conjugate action. Now, if I think about that carefully, what that really means is that I've got an equivariant element of H2 of G with values in the circle. And by the usual dimension reduction, that can go to an H3 element. So this suggests that the original H3 up here, which is my analog of the level for finite groups, is really an H3 obstruction. That immediately tells me I've got a Dixmuir-Duadie bundle of compact operators. That means I should really be thinking in terms of K-theory. So the meaning of this K-theory then would be bundles over G, which are equivariant in this sense of G by the conjugate action, but it's twisted by this cocycle omega, which I can represent diagrammatically like this. So that's what I mean by twisted K-theory. Okay, then everything I said in the subfactor picture has a meaning in the finite group case. So, for example, suppose you wanted to understand the analog of finite groups. So what's the meaning of this picture, K-theoretically? So the analog of a conformal embedding is a mapping from my original group G to another group L, which actually has to be surjective for this to work. And then, if I want to write down a modular invariant, I've just got to take this notion of restriction, because that's all I needed to construct modular invariance here was the notion of restriction. And you can do that just because you can take a bundle over L, equivariant over L. You can then pull it back to G, so you get a bundle over G. And by using the homomorphism from G to L, you can then let G act on that bundle pulled back. So this is a very simple operation, this sigma restriction. You can write it down in terms of irreducibles like this. But of course, the really interesting question is the opposite, is the John's alpha induction. That you can describe as follows. But in that case, I need to use quite a large K group to describe this full system up here. I've written it like this, where H is basically the pullback of the diagonal to here using L. So H is the kernel of this composition here, which takes AB to AB inverse pushed forward with pi. That gives me a subgroup of G cross G. H acts on the left and on the right. That gives me a K group, which is actually this full system here. And then all the notions of alpha induction have descriptions in terms of these much larger K groups. For example, the intersection of these two K groups, which would be the blue part, is exactly this extended system here. Right, so that is fairly simple in the finite group case, but it gets more of an issue in infinite groups. So I'll say a word about what I mean by twisted K theory for compact Lie groups. So the simplest way to motivate it is through understanding the K theory of the torus. So the K theory of the torus in K0 and K1 is just the integers, but let's compute it from first principles using Mea via torus. So these are just half interval. These are intervals. These are copies of the real line here. So K1 of both of them is the integers. So the only non-zero map here is the map gamma, which goes from z plus z to z plus z with these connecting map here. So if I want to compute K0 and KT and the K1, I just take the kernel and the co-kernel of this map. And of course I just get exactly what I should get, the integers. If I throw in an equivariant action of T acting on itself, now in this case I'm just talking about the adjoint action, so I just mean no action at all. The group is abelian, so it doesn't interfere. The group down here does not interfere with the space. So I just replace Z by a copy of the representation ring of T. Okay, but twisted K-theory allows me to change the connecting maps. So I'm going to have some gluing over one of these connecting maps here with some factor a to the k coming in from the representation ring of T. If I have some correction here, then the kernel immediately gets killed and the co-kernel drops to this quotient here. And even though there's no way you can do this unless you have equivariant K-theory, because there's no way you can have non-trivial bundles without that. As soon as you have this action coming in, I have this factor coming in, and I can do that. So the point of the right-hand side is by using this cutoff here, this infinite dimensional group has gone down to a finite group labeled by these cyclic elements. Okay, so that's what you do in general. So in this case here, I've got some connecting map, which means that I've got a bundle of compacts lying over this space, and when I come back, I glue according to some unitary, which involves a non-trivial character. I can do the gluing in any way I want. Instead of having a jump of k at one point, I can separate the k points out symmetrically over the circle and have a jump of 1 at each point here. What that means is that I can insert these points consistently into the circle, and then the push forward from this K-theory to this one gives me the generators I had. So that means that originally I was thinking of the Valenda algebra in terms of representation rings, which was the picture I had over here, but over here I now have the Valenda algebra described by these points here. So I'll be able to switch back and forth between the group and the group dual by this kind of analysis. Okay, so similarly for SU2, you can write down bundles of compacts. So over each small part of the space, there's no twist possible. You've just got to understand what you mean by a jump of the action on the overlaps. Okay, so right. Okay, so to finish in a reasonable amount of time, I'll jump to this work with Terry Gannon. So I've said that in the finite group case, it's very easy to understand modular invariance through K-theory. So the challenge is to understand these SU2 modular invariants and beyond using K-theory, and then use K-theory tools to construct modular invariance. Okay, so here I've written down two modular invariants, D4 and D6. Right.
Enthusiasm machine.
Sure. Okay, so I've almost finished anyway. So, okay, so I've written down a couple of modular invariants here. So, for example, on the right, there's the E6 modular invariant, which I had before, and you can concretely construct it from conformal embeddings by putting SU2 into SP4 and taking the trivial modular invariant here and restricting to SU2. So you can do that in terms of Lie algebras. And the NIM-rep is the E6 graph, and the full graph, the full system, which is the NIM-rep for Z squared, has a picture like this. So it's really two copies of E6. So I'd like to understand this from K-theory. So the natural thing to do is to take the action of SU2 on SP4 using the conjugate action and analyze. So this is these are three pictures here representing the conjugacy classes in three examples. This is SU3, this is SP4, and this is G2. So in this picture over here, in the case of the circle, I had just had to make one cut and then understand how I jump over there. In this case, I need to jump over three portions. So in each sub-portion, I have trivial bundles, which I connect by some unitary, which affects a representation or a character of the stabilizer across this interface. So these pictures represent bundles of compacts over, say, SU3, and this would be SP4, and this is G2. So in the case of SP4, I've got an embedding of SU2 into here, so I'll be able to pull back this bundle to SU2. So that's the... I have a picture of cuts here which are telling me what the bundle picture is in the SP4 case. So the SU2 has to sit inside this SP4 in a certain way. And the line that I've drawn here represents the maximal torus of SU2 sitting inside here. So to understand how this bundle restricts to a bundle here, I've got to see how this maximal torus intersects the cuts in the original bundle up here. And if you do a careful count of the cuts and see what bundle it induces back on SU2, you get miraculously this number 10, which I had in the previous sheet from the Lie algebra theory. And similarly for SU2 into G2, this is the picture. There's a more complicated series of cuts, and again the number 28 comes out. So in other words, you can understand the bundle picture completely for these inclusions. Okay, so then you have to start computing the K-theory of SU2 on SP4 twisted by these bundles. Now you can actually, in this case, compute using spectral sequences to get the K-theory. There should be a twist there. And you get something that's very small. It's Z2 in 0 and 1. Which is far too small, because I'm looking for something of dimension 12. Okay, so we can start at the opposite direction. Instead of taking the complete action, we can build it up slowly using an orbit analysis. Okay, so SU2 acts on SP4, so there are different kinds of orbits with different kinds of stabilizers. So here I've written down all the stabilizers that appear in this orbit analysis. These are the infinite groups, SU2, O2, SO2. And then these are the finite stabilizer groups. Now you can first compute the K-theory of just using these infinite stabilizer groups. And you get some kind of picture like this. It's 0 in one dimension, Z4 in the other. Now that's already too small, but it's better than, at least it's better than Z2. And then to get the correct picture, this is what you do. You can compute the K-theory using all the orbit analysis apart from the generic orbits. And then you get the correct number of irreducible objects. So that is done piecewise, adding on these orbits one at a time. But I think that the most interesting thing coming out of this is that the finite stabilizer group, which appears in this orbit analysis, is E6, which is the binary version of the symmetries of this tetrahedron, which appears everywhere. So the E6 classification appears in a number of ways through the labeling of the modular invariant, but also through the labeling of the finite stabilizer group, which is a completely different ADE classification. So there seems to be some relation between these two classifications. Okay, I'll stop there.
Do you have any question or comment? Yeah. Okay, if not, that's answer.